So, hello all, we are back with session 2 of PLL Basics. In this session, we will go through the basic design parameters of each blocks of PLL. Here we will start with frequency divider, VCO, PFD, and charge pump, and finally we will derive the open loop and closed loop transfer function of PLL. So, we'll go one by one each block. Let's dive into frequency divider. So, frequency divider, a basic frequency divider can be a divide by 2, 4 in odd numbers. So we can take an example of this circuit. I think there is some mistake in this. If my cursor is visible, the signal will go from Q bar
Q bar.
Q bar
Correct.
to D. Okay, so from Q bar to D, it's a feedback signal. Suppose the input clock is a positive edge triggered clock, and so for each of two cycles of input clock, we'll get one ramp at Q. So how we'll get? Suppose a input clock is given to this D flip flop. So this Q bar will be 0 in that phase, and Q will be 1. So it will be 1 till the time it will get another positive edge. So effectively for one time period we are getting a high and then we are getting a low. So in terms of frequency, if we'll see, basically our input clock was divided by 2. So the output Q is basically a divide by 2. So this was this is one of basic frequency divider which we can see. So what is the most important factor in frequency divider which we will consider for designing our PLL? Since from our last discussion, let's dive into block diagram first. Okay, so this was our block diagram of PLL. So here we can see VCO clock is input to frequency divider and output of frequency divider is a feedback clock. So this frequency divider has one of the most important parameter which is called capital N, or division ratio you can say, which is called division factor. What is division factor? Division factor is basically this output clock divided by reference clock. Okay, why we are considering reference clock? Because for this feedback clock to be stable, for this negative feedback system to be stable, we need clock should be equal to feedback clock. So the time when reference clock is equal to feedback clock, at that time what will be the division ratio? That is the design parameter for frequency divider. So capital N, or division ratio of VCO frequency divider, can be defined. Suppose we have considered 25 megahertz as the input clock, maybe reference clock. So suppose 25 megahertz is our reference clock, and we have designed our PLL for 2 gigahertz. Why we need PLLs? As I discussed in last class, we need PLL to get a very high and stable frequency, because reference or crystal clock can generate only a low frequency clock. So in order to generate very stable and tuned and high frequency clock, we need PLL. So suppose our PLL is designed for 2 gigahertz for a reference clock of 25 megahertz. So in that case, what will be division ratio for a frequency divider? It will be 80. Okay. So one other parameter which is very important in case of frequency divider is jitter. So jitter, I will just start with one basic diagram. Uh, Suppose this was our clock. We will explain jitter in more detail in upcoming lecture. For this frequency division and clock output, I'm just explaining. So suppose there is a delay and some because of some factor, which can be a noise in the reference clock or a noise in VCO. So our rise and clock time period got adjusted by or got delayed. So this adjustment, maybe it can be delayed or it can be uh, faster. So this change in the rise time and fall time will inject unwanted noise in our PLL, which can be one of the most important factor to remove the tuning. Why we need PLL? Because we want to tune PLL to our desired frequency. If this kind of jitters will come in our frequency clock, then this jitter can disturb or can make our output frequency noisy. So jitter is one of the most important factor to be considered during PLL design. We'll discuss about this more in upcoming lectures. Jitter is in time domain. In frequency domain, we call it phase noise, which is PN. Okay, so we have discussed frequency divider. Its design ratio is its design parameter is a division factor, which is f out by reference clock. Next, we will go to VCO. So VCO is as we have discussed in last session also. VCO is called heart of PLL. So we should take utmost care while designing VCO, and we should go through. We'll go thoroughly through the VCO design parameters. So VCO, we will design VCO for a center frequency. As I have already told you, we have considered 2 gigahertz as our, as I told in last class, last slide, 2 gigahertz as our central frequency. So for that central frequency, so we can go here again. So VCO has input as V control and output as F out. Okay, so V control is a voltage input and F out is a frequency output. So in this case, the gain of VCO will have a unit of hertz per volt. Correct. So so center frequency is the design parameter. So this center frequency FC. Suppose this is our VCO block. So FC is the frequency for which it is designed, and VC is the voltage, the input voltage to VCO. Okay, this is our VCO again. But we cannot directly tune to this FC. We should design our VCO for a range of frequency which will finally tune to FC. So this frequency range is FH and FL. So FC will somewhere lie between FH and FL. Our FC will lie somewhere between FH and FL. Again, similarly, the control voltage is also not directly designed for, cannot be tuned because it's an internal voltage. You cannot directly feed it. So we'll design it for a range of control voltage, and finally we'll do some calibration to fine tune the voltage and center frequency. So this is also designed for a range of voltage VH and VL. So finally this VC will lie in between VH and VL. So this VCO, as I told, VCO gain is in hertz per volt. So VCO gain can be defined as higher range of frequency minus lower range of frequency divided by higher voltage range minus lower voltage range. Okay. So this is the gain of VCO. Again, So what will be our desired KVCO? We can derive, sorry, FVCO means output frequency of VCO. So we can modulate or convert this equation into this equation, where FVCO will be the VCO frequency, FC is the DC frequency, or you can say it as the frequency which is, or noise frequency you can say. Okay, any VCO should give some default or noise frequency. Okay, so we'll go more detail into this frequency. Okay, so basically in industries we will not design for a single frequency. After VCO there is another block called LO generator. So based on suppose our VCO frequency is 2 gigahertz, but our system needs frequency of 1 gigahertz or 2 gigahertz or 0.25 gigahertz. So in that case, we'll multiply or divide it by desired factor to get desired frequency or tune desired frequency. Okay, so let's dive more deeper into VCO and its functional. As we have explained, uh, so before VCO there is a block called uh, charge pump, which is fed by up and down signal. This charge pump, this current, up current is fed by up signal, and down current source is fed by down signal. So based on this up and down signal, this current source will be turned on or off. After this, there is a low pass filter. Then our VCO block comes. So any noise which is fed through this V control voltage can be passed on to VCO. Okay, so suppose some noise factor n gets added here. So this noise factor n, so VCO final, if we will consider DC frequency as 0, the final FVCO output is what? KVCO times V control plus n, which is n is noise. So if there is a small noise also, that will be multiplied by VCO gain, and it will shake our desired frequency. Shake in the sense, if we need a frequency F, it will generate a frequency F plus some noise frequency, F noise you say. So it will shake our desired frequency if there is a noise in VCO control voltage. So what can we do to avoid this noise? Can we lower our control voltage? No. Can we lower this factor? We don't have control over this. We have only control over this parameter KVCO, which is design parameter. So what we can do is, for our design we should target a lower KVCO, but we can't make it a lower KVCO, so that our whatever noise is generated in control voltage, it will be multiplied, but it won't affect that much to our frequency. So we should target a lower KVCO. Again, let's go to this charge pump. So this charge pump control voltage can also be controlled. If we look, so what is the charge pump? This will be basically a PMOS in upper section, and down lower section it can be a NMOS. So to reduce control voltage, if we want to reduce control voltage, so why I told we cannot control this control voltage, we cannot reduce this control voltage, and we can reduce KVCO because KVCO is a design parameter. So while designing we can control KVCO, but we don't have control over control voltage. How? So if we want to reduce control voltage, okay. So this NMOS, which is down lower side, this should go. This will go out of saturation region. How it will go out of saturation region? Because we are reducing the control voltage. In turn, this VDS will reduce. So if VDS will reduce, then this lower NMOS will go out of saturation region. In upward region, there is a PMOS. So if we'll increase control voltage too much, then this PMOS will go out of saturation again. That's why we don't have proper control over control voltage because it's an internal signal. Therefore we will have more control over this K VCO, and we will fine tune our K VCO to reduce VCO noise as much as possible. So as I discussed, there is some DC frequency also which gets added to K VCO times control voltage minus VC. Okay, so one more doubt can come. So we are generating a 20 gigahertz. Can we generate more like 20? So we have generated, sorry, we have generated 2 gigahertz. Can we generate 200 gigahertz out of this PLL? Answer is no. We can't generate a 2 gigahertz. It will give more frequency checking, and we don't have proper control on KVC because to generate 200 gigahertz of frequency, let's write here, to generate 2 gigahertz of frequency, we need to increase KVCO. As I told, if we will increase KVCO, our noise will come into picture. More noise will get added to the output frequency, which is again unwanted or undesired. And higher KVCO will give more jitter. As I told, jitter will introduce some unwanted frequency or undesired frequency, so which will create more frequency shaking. That's why we cannot generate a very high frequency also from PLL. We can generate a high frequency, but when we need a 200 gigahertz frequency, we'll simply use a multiplier of 100 to get a 200 gigahertz. So 2 gigahertz is output of our PLL. So we'll multiply with 100 to get 200 gigahertz of frequency. Okay. So next we'll take an example of how actually we'll take some numeric value to why we are focusing more on VCO is, as I already told, VCO is one of the most important block, so we should take utmost care while designing VCO. So let's take an example. Suppose our supply voltage is VDD, for which we are designing our VCO, is 1.8 volt. Okay, so before VCO, as you already know, there is a charge pump, then low pass filter, and finally low pass filter will generate a control voltage. So we'll design our charge pump. Charge pump can be designed for a voltage of VDD by 2, which gives you 1.98, 0.98, so 0.9, not 98. And suppose I want, as we have already discussed, we are designing our VCO for a center frequency of 2 gigahertz. Suppose I want a 2 gigahertz frequency, and suppose my uh, so for 2 gigahertz frequency, uh, what is the safe voltage, control voltage? Safe meaning our VDD is 1.8 volt. So any safe voltage can be, means maximum voltage which is safer can is a VDD by 2, that is zero point 0.9. So we are designing a VCO for a zero point 0.9 volt of control voltage to get an output of 2 gigahertz. So as I told, we cannot target directly these voltage and these frequency. We design our VCO for a range of frequency and for a range of control voltage. Suppose the starting, we'll design our VCO for a range of plus minus 25%. Plus minus 25% meaning what? Our VCO is designed for plus minus 25%. So 2 gigahertz minus 25% of 2 gigahertz is what? 1.5 gigahertz is our lower frequency. Again, higher frequency is what? 2 gigahertz plus 25% of 2 gigahertz, which is what? 2.5 gigahertz, right? So 2.5 gigahertz. Again, similar for voltage. What will be our lower range of voltage? Zero point 0.9 minus, it will 25% will be some 0.7 nearby. I am approximating. Again, higher voltage will be 1.1. Okay, so based on these numbers, as we have already discussed, KVCO formula is what? FH minus FL divided by VH minus VL. Okay, so if we'll put everything in the gain formula, we'll get the gain of our VCO as 2.5 gigahertz per volt is our gain. So this is gigahertz. If we'll convert it into radians, how can we convert it into radians? We'll multiply it by 2 pi. So this will be converted to radians. So it will be somewhere around 15.7 radians per second per volt. Okay. So one more thing which I want to discuss in this ratio is this supply differences. I told we are designing our PLL for 1.8, but we have designed our charge pump for zero point 0.9. So there are basically two kinds of supply in any analog circuit design. So one is our core voltage and one is our IO voltage. So core voltage is basically the internal voltage or circuit voltage, which can be lower, and one is our IO voltage, which basically comes from PMU blocks. So this 1.8 is our IO voltage, and zero point 0.9 is our core voltage. Okay, so basically we will design our charge pump and PFD with, mostly we'll design our charge pump. Here I have told we are designing with zero point 0.8, but we will design our charge pump with IO supply. Sorry, this IO supply charge pump. Why? Because this is a more stable voltage which is coming from BGR, and this is internal voltage which have shaking, which will have our shaking effect, and which may change our frequency. But this voltage is directly coming from, this is a stable DC voltage which is directly coming from PME block. So mostly we'll try to design our charge pump plus after charge pump is LPF. So all this is very more important block, and our DC voltage should not shake and it should be stable. So mostly we'll try to design our all these internal blocks with IO voltage, and all other blocks will design with 4 voltage. Okay. So so here we will end our VCO parameters, and then we'll go to PFD and charge pump parameters. So as I told before VCO, there was a charge pump and loop filter. and then VCO. So, and before charge pump, there is PFD. This block diagram you should have in mind. Whenever we are discussing anything, this block diagram you should have in mind. So now we have discussed this frequency divider parameter, VCO parameter, and loop filter is basically RNC filter. So we'll focus less on this. We'll focus now on PFD and charge pump parameter. Loop filter is a basic RC filter you can consider. So let's now deep dive into PFD and charge pump parameters. So what does a PFD do? So PFD has two clocks as input, reference clock and feedback clock. Suppose this is our first clock is our reference clock, second clock is feedback clock. So what will PFD do? It will do find out the phase difference between reference clock and feedback clock, and it will give a phase shift. So what can be the maximum phase shift between any two signal? Invert, right? Maximum phase shift is 180 degree. So if we'll do plus and minus, so the phase shift should always lie between minus pi to plus pi. Okay, minus pi to plus pi. Okay, but after PFD there is a charge pump block, and this charge pump block works in time domain. So we should calculate delta t. So what will be the equivalent delta t for delta phi? We can use this formula. Suppose t reference is the time period for our reference clock. So t reference will have a phase shift of maximum minus pi to plus pi, that is 2 pi. So for delta pi, how much phase difference? Delta t time, how much? So for delta phi phase difference, how what will be the delta t? So basically, we have converted this phase difference in time domain, because after our because we want to analyze our circuit in time domain rather than analyzing in frequency domain. So this PFD will generate a phase difference delta phi, and that delta phi we have converted into delta t. So what is delta t? Delta t is t reference by 2 pi into delta phi. T reference is time period of our reference clock. T reference by delta t, sorry, T reference by uh, T reference, wait, wait. So, so our delta t is T reference by 2 pi into, sorry, 2 pi, T reference by 2 pi into the phase difference. So this is how we have calculated delta t out of delta phi. Same, okay, I will repeat this again. So what PFD does, it calculates phase difference between reference clock and feedback clock. And that phase difference we have converted in time domain, because the other processing, because after this there is charge pump, which works all the circuits we want to analyze in charge time domain. So this delta t is basically okay. So this PFD after comparison will generate up signal and down signal, which we have discussed in last class. So mostly up signal plays a very important role rather than down signal. So this is the up signal, and what is this delta t? This is delta t, the time duration for which our up signal is high. Okay. So why I have told why we have converted our phase difference in time domain is to have a proper realization of circuit in time domain. So this is the up signal, and this is delta t of up signal. Okay. So for this time duration, our charge pump we have discussed already. This was our charge pump, right? This was our charge pump. So for delta time duration, this up signal will be high, and it will charge our LPF. It will charge our LPF for delta t time. Okay. So now our more objective is how much current it is going to pass. So that we can say tell as average current. So how to calculate that average current which is passed to charge pump? So I average. So we are designing our charge pump suppose for a ICP. What is ICP? It is a current which will flow for one time period. So how can we get average current? Average current which is actually flowing into our low pass filter. After charge pump there is low pass filter, and this low pass filter will convert our charge pump current into voltage which is finally fed to VCO. So average current, how average current which is fed back to PDF. Okay, so this charge pump will give some average current. Okay, we'll calculate this average current. I average. How can we calculate I average? We have designed our, so ICP is parameter for, ICP is design parameter for charge pump, KVCO is design parameter for VCO, N is design parameter for frequency divider as we have discussed till now. Okay, so now we wanted to calculate gain. Sorry, why we want to calculate this all this thing, why we want to calculate, but because we want to calculate the gain of this block, PFD plus charge pump. So what is output of this whole block is average current. What is input of this whole block is the phase difference. Correct? Phase difference which is fed back, right? So this block is phase difference. So if we'll assume it as a block, so this block is having phase difference as input and average current as output, which is fed back to low pass filter. So we have to calculate average current and phase difference, and we will divide the ratios to get K PFD plus charge pump. Basically, this is gain of PFD plus charge pump. Correct. So how I average is calculated? As we told, this charge pump will be charged for delta T time. Okay, and total time period is T reference. So delta T by T reference and our charge delta T by T reference, and since our charge pump has a ICP current for one time period, so it will multiply this by ICP, we'll get our average current. Correct. So this is our average current which we are getting out of charge pump. Since we have already calculated delta T, what is delta T? How we got delta T? We have converted uh, we have converted the phase difference between these two clock in time domain, and we got delta T. Delta T is the time for which we are getting up signal on, and from this up signal we have got a current. Since our charge pump is designed for ICP and we want to get the actual current which is flowing out of charge pump to low pass filter, that is delta T by T reference into ICP. So we now got I average. Okay. Now what we will do, we want to calculate I average by delta phi to get our gain of PFD plus charge pump. So this was our I average which was flowing to low pass filter. Now we will substitute this delta t into this first formula. So when we'll substitute this delta t here, we'll get this equation. This you can do and discuss. This you can do and take check. When we'll replace delta t by this formula, t reference by 2 pi into delta phi, we'll get another form of our first equation, and this delta phi will take other side. So finally what we will get is I average by delta phi is what? Nothing but ICP I forgot to write final formula, so I will write it here. So from this equation, how we'll get our final KVCO plus charge pump gain is, so sorry, sorry for bad handwriting. K PFD plus charge pump is nothing but I average by delta phi, correct? Average current by phase difference, which is nothing but IC. Finally, when we will substitute everything in that formula, we'll get ice charge pump by 2 pi. Okay, so this is our final gain of these two blocks. What is gain of these two blocks? ICP by 2 pi, which you can realize here also. If you will see here, uh, divide I average by delta phi and replace this T reference in terms of ICP. So finally you will get KPFD as ICP by 2 pi. KPFD plus charge pump is ICP by 2 pi. So now we have got the gain for KVCO. Now we have got a factor for our charge pump plus PFD. Now we know frequency divider parameter. So now we have almost everything to get the transfer function of PLL. One more thing I wanted to discuss about this charge pump is, okay, this charge pump, how it works in. So basically, if anyone wants to understand, they can write an equation for this charge pump. So what will be the any capacitor? Okay, will realize this current is flowing through this low pass filter. Basically, average current which we have calculated is flowing through this capacitor. So how much instantaneous voltage will be stored? Now we are analyzing this low pass filter. We have analyzed almost all the block. Only low pass filter is remaining, which is this block. This block. Okay. So for a delta I current, how much voltage will be generated? Suppose since I have supposed it as I have assumed it as a low RC filter, so delta V voltage will be what? I into R plus I into delta T by C. Correct. IR into IDT by C. Okay. How we got this? We know the basic current equation I equal to C dV by dt, right? Through any capacitor. Basically, change in voltage will generate a current through capacitor. From this, we got this. So, this is the change in voltage across low pass filter. Okay. So now we'll dive into the calculation of open loop transfer function of VCO. Now we have almost all the parameters which is required for getting the transfer function of this VCO. Okay. So, and we want all these equations in terms of frequency domain. So, how we'll get time domain to frequency domain is we'll do Laplace transform or in S domain we can get, right. So, next slide focuses on open loop transfer function of PFD. So, as we have discussed, the charge pump plus PFD is having I charge pump by 2 pi as a design parameter, which we have already derived. Then this loop filter is basically a RC filter. So this is any basic RC filter which will have transfer function just like this. Another thing is this KVCO. When KVCO is transformed into frequency domain, it will become KVCO by S. Another parameter is frequency divider, which is 1 by n, basically 1 by n. So when we'll substitute all these three, KPFD plus charge pump, then loop filter, then KVCO, then frequency divider. After substituting each and every term and assuming the constant terms as k, you'll get second order transfer function, open loop transfer function of VCO. Okay, so basically VCO, sorry, of PLL. So what this denotes is our PLL is a two-pole transfer function. Sorry, two-pole control system because it's basically a negative feedback system, right? So from this equation we can say our PLL is a two-pole control system. Where what is the location of two poles? Both poles are at zero. Okay, let's go into the closed loop transfer function. So closed loop transfer function is nothing but open loop transfer function divided by 1 plus ls divided by 1 plus ls. So we'll substitute all the terms which we got in last slide, means ls, and we'll get this as our. If it is not visible, I can zoom it more. Hope it's visible now. So this is the closed loop transfer function. How we got closed loop transfer function? Open loop transfer function divided by 1 plus open loop transfer function. So when we'll equate this with a standard open loop second order closed loop system, which is nothing but omega n square divided by s square plus 2 zeta and s plus omega n square, and we'll compare these terms and we'll get all the factors. So we'll get omega n, which is nothing but natural frequency, and we'll compare this with 2 zeta omega n, which is nothing but krc. From all these equations, we'll generate the parameters for loop filter. Why we are getting this, why we want this is to finally put the values for resistor and capacitors for our loop filter. So from all this, after solving this damping factor equation, we'll get the equation for R, which is the resistor of loop filter. Then, since we know this charge pump equation, ICP equal to 2 pi divided by K and omega, sorry, omega n square divided by KVCO. So from here, again when we'll, okay, here I again forward. So now our we have two circuit elements in loop filter. We got R. Now our aim is to get C. Okay, so we'll discuss here how we will get C. So we, as we have seen, R is nothing but 2 zeta 2 zeta by C1 into omega n. Okay, so how can we get this C1? So for this we have to assume something, right? Either we can assume R or we can assume Cn. So for proper stability of signal, any system control system, we assume zeta as 0.7, and as we have already, and we already know from the last equation, last discussions, our reference frequency was 2.5, for which we are designing our PLL is 25 megahertz. Sorry, and we'll keep natural frequency as a reference frequency divided by 20, Why we are keeping 20? We'll discuss it in come just now. We can divide it by any factor, right? Why we are, or we can directly keep natural frequency same as reference frequency. What is reference frequency? Again, just for clarity, I'm going again. This is the reference clock, and frequency of this clock is reference frequency. But we are keeping natural frequency as 1 by 28th time of reference clock. Why we are keeping this? Because if we'll keep natural frequency as same as reference frequency, then the PLL will give clocks very rapidly. Because if our PLL will give clock as soon as reference frequency comes, so it will charge and discharge very soon, and it will won't get sufficient time to complete a full cycle, and it will create a unwanted oscillation, unwanted noise, which is jitter. So in order to avoid and make our PLL proper fully stable, the natural frequency is assumed as 1/28 times of reference clock. So now we have to assume C1. Either we can assume R or C1. So we have assumed C1 as 20 picofarads. So from all these equation, now we can get the value of R. You can calculate from your side. I will write final values in final slide. So now we have R and C1. Now we can get 0 by comparing the standard equation with our formal equation which we have derived. We can get zeros too. So our 0 will be nothing but 1 by 2 pi R C1. We already have calculated R and assumed C1. So we will substitute R and C1 here to get the zeros. And our poles, as we have discussed, is all at 0. Pole is all at 0 frequency. Both the poles are at 0, which we have already calculated from open loop transfer function. If we'll equate this to 0, we'll get both the S values as 0. So finally, we got all the design parameter values which is needed for designing a PLL. Now we'll summarize and we are designing a PLL for 2 gigahertz of frequency, 2 gigahertz of output frequency. So I have just summarized all our calculated values here in the table. We have assumed this reference frequency or input frequency is 25, and we are designing a PLL for 2 GHz frequency, from which we got 80 as division ratio. We have assumed control voltage as 0.9 volt, from where we got KVCO. Then we have derived R, C1 we have assumed. Then we have derived ICP, and then we have then we have also derived KPFD plus charge pump, which is nothing but ICP by 2 pi, and we have assumed bandwidth as 25 megahertz by 20, basically 1/28th time of reference frequency, and then we have calculated poles and zeros. So this full summary we have discussed till now. Again, this left hand side is basic industry PLL specs, which you can go through for your understanding. So this is a standard, you can say, PLL design specs, which I have taken from some design. Okay, so now we have almost all the design parameters. So in next class we will go through AC and transient modeling of PLL, and then we will go design of each blocks one by one. So if Ranjan, if you have any doubt, we can discuss it or we can wind up the session. Okay. Okay. Thank you, Ranjan. Thank you for attending session.